So I'll assume that all of you have already had a practical session this week and you have your groups formed. So I'll go directly into the milestone 1 code. So your milestone 1 from the top level should look like this. So you have the read-only streets database library. This library is the API that allows you to access data about the map. You have the main executable that's run whenever you run your program. And there's the tester executable that's your auto tester. And you can use the auto tester to test the functionality and performance of your code. Both the main executable and the tester executable are already implemented. Calls the load map and close map in the street map library. The street map library is what you need to implement in milestone 1. This serves as a wrapper to the actual streets database library to do the load, close queries, and everything else that's related to accessing the map. So to start with milestone 1, first, very seriously read the handout from top to the bottom. Every single line of the handout is important. And most of the questions the TA will get from students are on the handout. You will need at least one global variable to pass the performance tests. And you will be choosing containers from the STL to store the global variables. And I'll be showing that to you in the exercise in this tutorial, in the example. Breaking maps up into parts. This is how the maps are stored in the database API. You have intersections. Each intersection has an intersection ID that ranges from 0 to number of intersections minus 1. So it's a continuous range. Intersections are connected by street segments. Each street segment has a street segment ID that goes from 0 to number of street segment minus 1, also a continuous range. And you have some other entities like streets. Multiple street segments will form a street, and each street has a street ID. In the map, you can treat the intersections as nodes in a graph, the street segments as edges in a graph, and they're connected together. What you're given, there is the load map function that's called whenever you start a map, whenever you open up a map. And there's the close map, that's called whenever you close up a map. Usually you load some data structures in load map and you clean up after yourself in close map. For milestone 1, after you call ECE297 init, without any modifications to the code, compile and run ECE297 exercise 1. You will get something like this because there's no modifications to the code. You will get build errors saying there are undefined reference to some of the functions. And these functions are defined in m1.h. m1.h is a very important header file that has all the specification of what to do. Read it thoroughly from top to the bottom. All the code, all of the comments. For each of the function headers inside here, there's a comment saying what this function should do, and there's a speed requirement for each of the functions. In this tutorial, I'll be using this function as an example. Find street segments of intersection. that returns the three segments for the given intersection. And to get over from the build errors, you should be creating empty stop implementations of all of the functions listed in m1.h. So for each function, just don't write anything. If it's returning some number, return 0. If it's returning some vector, return an empty vector. Just to write placeholders for all of the functions to get over through the build errors. And so that you can see all of the tests without having to implement the functions themselves. So currently, because we don't have any implementations of the functions, all the tests should be failing. We have functionality tests that are used for checking whether the implementation is correct. We have performance tests that are used for checking whether you are taking a long time to run the functions or not. There is a performance test for load maps, but it's loose enough so that you can complete everything inside it. Valgrind tests for memory leaks. And your goal for milestone 1 is to pass all of the tests here. Now let's go into the example function that we are going to cover in this tutorial. You're free to use any code provided in this tutorial in your code, but you'll likely need to modify something for coding style. So this function, in the function specification, it needs to return a vector of the three segments connected to an intersection. So the return is a vector of street segment index. It takes in intersection index for a single intersection. And you need to obtain all of the street segment IDs connected to that intersection. Our only input is the intersection ID. So we need to access something that's outside the scope of this function. And this is where you need to start reading the streets database API.h. This is also very important for you to read from top to bottom. For example, each entity in the map has something like a info struct to store whatever needs to be stored for that entity. For a street segment, it has the OSM ID. The OSM ID is different from the street segment ID. Street segment ID goes from 0 to number of street segments -1, and it's a continuous range. OSM ID is a universally unique ID that's given to each entity in the maps. And it's universally unique across all maps, all entities. So it's a huge number. Intersection index from and to, each street segment connects two intersections. The one-way Boolean signifying is if this street segment is one way. Number of curve points in the street segment, the speed limit, and the street ID that this street segment belongs to. And this is just an example. Other functions that might be related to the function we're implementing: get non-intersection street segment takes in intersection ID, and it returns the number of street segments connected to the intersection. Get intersection street segment takes in the intersection ID and the segment number. The segment number goes from 0 to whatever is returned from this function, -1. And this returns the street segment ID of that street segment. You can then get the street segment info struct using this function and the street segment ID. In general, the street database API naming convention is that for a lookup, which is usually O1, starts with a get. The first word is the entity that we are looking at. So in this case, it's given an intersection ID. So we are looking for something related to intersection. And in this case, it's the number of street segments connected to this intersection. So for example, for the intersection that's at St. George and Galbraith, this intersection ID is 232, and it has 3 street segments connected to it. So we call get num intersection street segment 232 should return 3 for 3 street segments. Then we call the get intersection street segment 3 times for 012. And the intersection ID is 232, and this should return the 3 street segment IDs. We can then use the street segment IDs to get the struct street segment info, for example, or we can do whatever we need with it. Just be careful that even though you're seeing intersection ID, street segment ID as different types, by the compiler, it will only see them as int because they are all type defs to int. So even if you accidentally mixed the usage of some of these, the compiler won't notice. So it's very hard to debug in that case. So as part of your coding style guide, use descriptive variable names to avoid mixing the usage of street segment ID and intersection ID. So if you're naming something that's of type street segment ID, make sure the name has something related to street segment in it. And same for intersection ID. Make sure your name has something related to intersection in it. And you should be unifying this within your group. Now let's try implementing this function, given the functions to use here. Any ideas on how to start with this function? Remember, we want to fill this return vector with the street segment IDs that are connected to the intersection. And the intersection indexes passed in. Let's open up a text editor or anything to start thinking how to do this. You'll likely need to use some of these functions, right? Let's continue. So you first call get num intersection street segment intersection ID to get the number of street segments connected to the intersection. You loop from 0 to that number -1 in a for loop. And in each iteration, you call get intersection street segment intersection ID and I to get the actual street segment index. And because we just need the street segment index, we just directly push that back into the vector, into the return vector. In this case, we don't need to get the street segment info. And in this case, we just need to do this rather than going through all of the street segments. And if we just run the tester related to the intersection, we can do it using this syntax. ECE297 exercise 1 -- run tester. And the star intersection star tells the tester to only run the tests that have intersection in the name. And in this case, you should be passing the functionality test, but failing the performance test. And this means that this function is not fast enough for our performance requirement. In M1.h, we have this chunk of comment that's defining the different levels of speed requirements. For a high speed requirement means that this function must be very fast and you'll need to create some data structures to rapidly return the right data rather than just building the vector itself inside the function. Moderate, this function is speed tested, but you can do it in a more straightforward way, like what we just did. Now, this function is not speed tested. For the function that we're implementing, we need to do a high speed requirement. So given that all of the get functions to the street database API are all one, what is the complexity of this function? Yeah. ON or OK. We use K because it's not actually a defined N, and it's not a very big N. It's a smaller K that's an average number of street segments being connected to each intersection. How can we speed up our function then? In m1.cpp, you have this comment inside load map. Load your map related data structures here. So this means that we need to do some data pre-processing before that function was called. And load map is called before all the other functions are called. So this is the perfect place for you to do all of the data processing. What data structure can we use for the intersection street segments? We don't want to build the vector to the return vector inside that function now. We want to build it beforehand. So for the input, we're taking an intersection ID as an input. This is an int that is of a continuous range from 0 to number of intersections -1. The output is a vector of integers. That's the collection of street segment IDs. And here is a list of the STL data structures that we can use in this case. We have the vector that takes in the integer index. Output is a template type. List, input is iterator, output is template type. map and unloader map that takes in templated keys and output templated values. Which of these data structures can be accessed with an integer intersection ID? Which one of those? Or one or more of those? Technically, all of them. What can these data structures contain? Anything, because they're template types, including vectors of integers. What is the complexity of accessing elements in the data structure? We have the list of timing complexities for each of them. Vector is an array, it's all one. List is a bidirectional linked list, that's ON. Map is a binary search tree, that's O log n. Our map is a hash table, that's O1. So in this case, we are choosing from vector and unloader map that are both O1s. But if we look at the underlying logic for both of them, for a vector, an access to a single element inside the vector is a direct memory access. So we're doing a load instruction using the start address of the first element and an offset. That's a single load instruction. For a hash table, we have to first call a hash function to get an index, and then a direct memory access. And because of the hash function, it takes time. So in general, unloader map is a bit slower than vector. So in this case, vectors are indexed using a number, and if your input number is a continuous range from 0 to size -1, nothing can beat a vector. So in this case, we choose the vector because we are indexed using the intersection index. If the input is not an index, like if we need to look up with a name that's a string or something that's just not a integer, use a hash function. Use the unloader map. Or if we are looking up with a really big number that is not continuous, like the OSM ID, because it's enormous, it is unique universally, and it has most of the entries empty. It is very wasteful to use vectors in this case. So use unloader map. For the function we're implementing, we choose vector in this case. So your global variable will be a vector of 3-segment ID. What this looks like in memory, you will have a vector that goes from 0 to a number of intersections -1. Each of them contains a vector of integer, and the vector of integer contains, for each intersection that's indexed using this index, it contains the street segment IDs connected to it. So if you need to access the street segment IDs for intersection 1, just do intersection street segments square bracket 1. And that's the vector itself. And how would you populate this global variable at the beginning? So this line, load streets database bin map name, opens up the map that you're looking at. And this will return false if the map is not opened correctly. First, do a resize of the global variable, the outer vector, to be the number of intersections because the outer vector is indexed using the intersection IDs. So we resize that to the number of intersections. And this command creates empty vectors for each intersection at the beginning. We then do a for loop that loops through all of the intersections. For each intersection, we do the same code as we did in the function before. We get the number of street segments connected to the intersection. We loop through it and we get the street segment IDs using the get intersection street segment function. We push it back into the vector at intersection street segments indexed by intersection ID. Is this clear? You can do this afterwards. Then the actual find function is just a single line of return. Returns the intersection street segments indexed by intersection ID. And this is the vector that we are looking for. So in this case, we move the complexity of the function into load map. So your function should pass the performance test in this case. And don't panic if you don't see the pass after you did what I just did, because there are 3 tests in each of the intersection tests. We're just showing this so that you can see it passing. And Minder is a performance test for load map 2, but it has several seconds to load everything into your data structures. It should be more than enough to do whatever you need. Just make sure you're not abusing this time to do something crazy like duplicated code, doing something that's not necessary. Okay, and that's the end of this tutorial. I have put the link to the tutorial on how to resolve git conflict under the tutorial 3 page on Quarkus. So make sure you go through that and don't have any git conflict issues towards the end of milestone 1. Make sure you resolve all the issues at the beginning so that you're not panicking at the end. Any questions for me? No? Okay.